All right, so for the second part of this lesson, we're essentially going to, work on determining limits. So for that, we're going to need to go over some properties because we're going to be having to apply combinations of properties for certain functions in order to make, determining the limit a lot easier. So here we have that the limit of f of x as x approaches c will be infinity, and that the limit of g of x as x approaches c will be equal to L, where L and C are real numbers. And the first property is a sum or difference one. So when you add or subtract these two functions, you're going to get infinity. It's basically saying, infinity plus any number will still be infinity, which, makes sense. The product is the same, and when you multiply infinity by any number, by L, it could be 10, it could be 20, it's still going to give you infinity. So again, pretty intuitive, and this is for when L is positive. Now, if L is negative, when you multiply the limit of f of x as x approaches c by the limit of g of x as x approaches c, so infinity by some negative number, you're going to get negative infinity. And the last one is saying that when you divide any number by infinity, because remember g is a number and f of x is, so this will be infinity, you're going to get 0, which makes sense again, because any number divided by a huge number will essentially be like nothing. So these are pretty intuitive. So now let's go ahead and let's apply them. So let's figure out the limits for these two expressions where they're the same function, but we're just looking at the one side of the limit as x approaches 1 from the negative side here, and as x approaches 1 from the positive side over here. So we know that let's say let's call this f of x. F of x. We know it's undefined at x equals 1. And so that means there's going to be a vertical asymptote there because we can't cancel anything out. So let's just draw a sketch to get an idea of what's going on. So we know we have a vertical asymptote of x equals 1. We want to see what's going on the right side and the left side of this asymptote. So the idea is just to recognize that if you just plug a number very, very close to 1 to the left, so something, less than 1, like 0.99999 into the equation, you're going to get an idea of if that number is going to be very, very small or very, very huge. And likewise, you can plug a number very, very close to 1, but slightly greater, like 1.0001, and we could see if that number is very large or very small. So, let's go ahead. Let's just do that. So let's look at the left side limit. So we would have, let's say we have x is on the left side. We would have x is 0.99999. Let's literally evaluate that. It's a little tedious, but it won't be too bad. 0.999. How many 9? I think with 5. Squared minus 3 times 0.99999. We're going to divide that by 0.99999 minus 1. And see, we get about 200,000. So when we have that, y is, 199,999. So that essentially tells us when we're on the left side of the graph, the function gets super, super large. It blows up. Now we could, figure out exactly what values it goes through, and you're actually going to find that, if you actually plugged in 0 into here, you get 0. So we know it goes through the origin. The graph is essentially doing something like this. So then this tells us that the limit as x approaches 1 from the negative side of f of x is going to be positive infinity. So now let's see what's going on with the right-hand limit. So we're going to now just plug in like a number very, very close to 1, a little bit larger. Let's pick like 1.00001, and let's see what value it would get. So we're going to go 1.00001 squared minus 3 times 1.00001. And we'll divide that by 1.00001 minus 1. And we see we get a very large negative number. You get y is negative 200,001. And so then this tells us the values are getting very, very small. And the graph goes, because yeah, we has a y and it has an x-intercept of 3. So, you know, it's going to do something like this. Again, we don't really care yet about figuring out the details of the graph. We just care about the behavior of the limit as the graph, you know, approaches this asymptote. So we can say now the limit as x approaches 1 from the positive side of f of x is equal to negative infinity. All right, let's look at another one. So here we have the limit of 2x over x minus 3 as x approaches 3 from the negative side and from the positive side. So same idea. We know this is going to be, you know, undefined for x equals 3. So we know the graph is going to have an asymptote of x equals 3. So we want to see what's going on as we get very close to this asymptote from the right side and from the left side. So again, we just plug values very, very close to it, slightly smaller than 3 and slightly larger than 3. So we can pick like, from the left, we can pick 2.9999, 2.9999. And from the right, we can check, you know, x equals 3.00001. We just plug that into there and see what we get. So we do 2 times 2.9999 divided by 2.9999 minus 3. We get about almost negative 60,000, negative 59,998. Now let's see what would happen if we plugged in 3.001 into here. So we got then 2 times 3.00001 divided by 3.0001, oh, whoops, 01 minus 3, and we get 600,002. Oh, I see. I made this one longer than normal. I was wondering why it was so much bigger, but in any case, we can see that this is going to be approaching infinity from the positive side and negative infinity from the negative side. So our graph is going to do something like this. And this one also goes to the origin. Graph will be going that way, and then this way on this side. Whoops, or like that. So then we say its limit as x approaches 3 from the negative side of f of x. In this case, it will be negative infinity. And this one, the limit as x approaches 3 from the positive side of f of x will be positive infinity. Okay, so now let's finish off with just a couple more examples of how we can figure out limits. So here we have the natural log function, and we're trying to find the limit as x approaches 0 from the positive side. Now you should know what this graph looks like. If not, make sure you review this because this is gonna pop up a lot in calculus. And these tend to pop up at the worst times. You definitely will have these on your AP exam. So the natural log function, it's gonna do this. It's basically gonna look like this. So let me just make it in pink. So we're talking about, it's going, towards 0 only from one side, and it's going, it's getting very, very small, but it's getting infinitely, negative. So it essentially has an asymptote at x equals 0 because it's not defined for 0. So then this we could just say, this is just equal to negative infinity. So it's pretty straightforward as long as you know the graph, because we're going, again, infinitely downward. Okay, now here the limit of this entire expression of 1 plus 1 over x squared. So here's an example. We're going to use the sum or difference property. So we can make this equal to two limits. The limit as x approaches 0 of just the constant value 1 added to the limit as x approaches 0 for the function 1 over x squared. Now, since this is a constant, the limit is just be 1, and it's not going to be affected by the x value. That would just be 1. And this, if you remember our graph, well, it's going to basically be infinity, because the graph of 1 over x squared, looks like a cone. At least if I could pop back to it if we have a quick picture. Well, let me just sketch it again in case you forget, but you should know what this graph looks like. So the graph of 1 over x squared looks like this. So when it's approaching 0 from both sides, the graph gets infinitely large, so the limit is infinity. So we have 1 plus infinity, and we know from the theorem that we learned, any number plus infinity will just be infinity. And next one. Okay, here we have something that maybe can look a little complicated, but it's actually pretty simple. What we're going to do is we're going to break this into two expressions. So we're going to take the limit of the top. So let's look at this like this. The limit of x squared plus 1 as x approaches 1 from the negative side, all over the limit of the cotangent of pi x as x approaches 1 from the negative side. and we evaluate them individually, then divide. This is another property we can do when we, the quotient property. Now, this is just a parabola, and this we could just use direct substitution. We could just plug in 1 for x, and we would get 1 plus 1, and we would, get 2 on top. Now here, let's remember what the cotangent graph looks like, but let's also keep in mind that we're just plugging in 1 for x, so we're looking at essentially the cotangent of pi. Now let's pop back to our graph we just did in the previous part of the lesson. Cotangent of pi is not defined, but the limit as it approaches pi from the negative side, and we're coming on this end, is going to be negative infinity because we're coming, we're going downwards. So and that's actually just write it like this. So the limit as the limit of the cotangent of pi as we approach it from the negative side will be negative infinity. So we have 2 divided by negative infinity. And again, our property tells us any number when we divide by infinity is just going to be 0. Any number divided by infinity, it's going to be basically nothing. Like you could have 1 billion divided by infinity, it's still, nothing. It's still relatively small compared to it. All right, now let's look at this one where we have the limit as x approaches 0 from the positive side of 3 times the cotangent of x. This we can use our product property where we break it into the limit as x approaches 0 from the positive side of just 3 times, so let's do that whole thing, times the limit as x approaches 0 from the positive side of the cotangent of x. Now this is a constant, so it doesn't change anything. It's just going to be 3. And again, the limit as x approaches 0 from the positive side of the cotangent function, it's going to be infinity. But let's just refer back to it in case you need a refresher. We're coming from the positive side, remember? So we're approaching this, but from this side. So we're coming along this line. And this will go infinitely large. So what we're going to have is essentially 3 times infinity, which will just be infinity. All right, and the last one we got, the limit as x approaches 0 from the negative side of x squared plus 1 over x. And this is just an example, another example of the sum property where we can break this into the limit as x approaches 0 from the negative side of just x squared plus the limit as x approaches 0 from the negative side of 1 over x. So evaluate those individually and then just add them up. Here we can just, apply direct substitution because we could just put 0 into this equation and now it would just be 0. So we have 0 there plus this graph 1 over 0. But again, this is going to have an asymptote, and this would actually be negative infinity. They're coming from a negative side. So you should remember, you recognize. Let's just draw a sketch of it again. What this graph looks like. It's going to look like a hyperbola going like that and like that. So since we're approaching 0 from the negative side, we're on this side of the parabola, or this side of the hyperbola. So we're going downwards towards negative infinity. So this will be negative infinity, so it'll be 0 plus a negative infinity, which will then just give us negative infinity. is our final answer. There we go. And that's all there is to it.